So next we're going to have Mark speaking, who's a second year PhD student from MathSys, and he's going to be talking about inferring from multiple in epidemics.
Cool, brilliant. Thanks for that, Andrew. So yeah, hi, I'm Mark, second year PhD in MathSys, and I'm just going to be talking a little bit today about the current state of my PhD project. This presentation will be split roughly into two halves. The title represents more so the second half. For the first half, we're more so concerned with different ways in which we can use game theoretic models to model social distancing in an epidemic. So the majority of this work is sort of influenced by this paper by a guy called Reluga on the game theory of social distancing in response to an epidemic, where he models epidemics as what's called a mean field game. The basic idea is that you've got this population of individuals, and these individuals are each seeking to make their own optimal choices, which we call kappa in this presentation, which usually represents how much they're socially distancing from other people. Now, of course, those optimal decisions are likely to be influenced by the behaviour of the population as well as the current state of the epidemic. If there's lots of infections, you might be less inclined to go outside, for example. But equally so, we can say that this population is made up of a bunch of these individuals, all of whom are seeking to make these optimal decisions as well. So there's a few different things that we need in order to encode this all up mathematically. First is some sort of disease model. Then it would be good to define what we mean by optimal choices. What are people optimizing? And then also, what do we mean by, quote, rational individuals? So for our disease model, I'm going to assume not everyone here is an epidemiologist. So just to go over one of the basic disease models. Here we take the SIR compartmental model, which essentially splits the population up into three different categories. You're either susceptible to the disease, infected by the disease, or recovered by the disease. And you can swap between these three classes by a transmission contact rate beta and this recovery rate gamma. And it's given by this system of ODEs over here. Of particular interest for this presentation is the idea of R0, the basic reproduction number. If anyone dares think back to COVID, they were waffling on about the R number constantly on the news. This is defined as the average number of secondary cases produced by an average infectious individual in a totally susceptible population. So the idea here is, say if the R number is 3, then that means if I'm infected by the disease, I am on average going to pass on that disease to 3 other people. So you can imagine at that point the disease is growing, but if the R number is, say, less than 1, then the disease will hopefully die out at that point. For this presentation, we don't exactly take this form of the SIR dynamics, we modify them slightly. So for simplicity, we just set the recovery rate as equal to 1, so our rate of transmission here is just equal to R0. What we're interested in is encoding some aspect of human behaviour into this. So we introduced this K parameter called the infectivity of the population. This is some aggregated mean of everyone in the population of how much they're social distancing. So this is normed at 1, and as people social distance more, K will decrease. And as you can imagine, as the infections die down, people will increase their infectivity, their social interactivity, in order to bring K back up to 1. So this is all well and good, but sadly we can't control the behaviour of the whole population. We can only control our own behaviour as an individual. So we can take an analogous set of ODEs, which instead of now keeping track of the proportion of the population, is now keeping track of the probability that you as an individual are either susceptible, infected, or recovered, given by psi. And what's important is that this K is now kappa. This is how much you as an individual are social distancing. So this is our big control parameter for this presentation, because this is what you as an individual can change. So that's the first thing, that's our disease model. Now it would be good to define exactly what do we mean by people making optimal decisions. So we say that each individual is seeking to maximize some utility function U that depends on both their own behavior and on the current state of the system, the epidemic. Here we take our utility as some integral over a payoff function or cost function V, and we take it as an integral because we assume people want to be making optimal decisions over the course of the whole pandemic. In terms of the idea of rationality of human behavior, we just take the basic equilibrium in game theory known as the Nash equilibrium, which is achieved when no individual in the population can change their behavior in order to further increase their own utility, given the behavior of the rest of the population. So the idea here is that I have my own personal costs, my own personal utilities, and I'm going to optimize for them. Then we say everyone else is doing that as well, and what equilibrium state do we end up in? Mathematically, this is done by setting our k, the infectivity of the population, which is just a mean of these kappas, as equal to kappa. But it's important to do this after optimizing. Ideally, what we want is we want some equation for kappa in terms of these other variables to say, right, how am I as an individual going to react to the state and the behavior of the population, and then assume everyone's acting the same. Bit of a crude assumption, but it's an equilibrium state and it's a good starting place. What would perhaps be helpful at this point is if we looked at a sort of specific form of this utility function. So this is a basic one we've been working with, which essentially says that individuals are seeking to minimize two different costs. First of all, we have some cost associated with being infected by a disease, given by alpha. And of course, you only have to suffer that cost if you are infected, hence the SII term. On the other hand, we say that there is some cost associated with social distancing, which I think makes sense because we want to be coming in person to in-person seminars as opposed to having to join online and wear masks and distance people in the shops. And we give this as some squared deviation from this given social norm kappa star, which we put it there for generality, but it's basically just equal to 1. So you can imagine it going like this. So as the course of the pandemic goes on, this cost of infection term will increase in most people as their probability of being infected increases. So what they do is they suffer the cost of social distancing by changing this kappa, because by changing your kappa, you're then going to decrease your probability of being infected from our disease model. So you're going to suffer some total cost over the pandemic for that to then hopefully minimize near the end. So in terms of maximizing this utility, we set it negative because these are costs, so we can maximize, and that's just slightly easier. When it comes to maximizing this, we can't just do it with respect to any old variables. They've got to obey the SIR dynamics that we defined earlier. So we can formulate our full constrained optimal control problem as seeking to maximize our utility by changing our behavior kappa, given the SIR dynamics, given some initial conditions to our system. So how do we go about solving such problems? Well, as it turns out, solving constrained optimal control problems of this form is exactly the same as optimizing for an unconstrained Lagrangian function. Now, again, I'm not going to assume that everyone here is an expert in Lagrangian mechanics. I wasn't before doing this PhD, nor was I in epidemiology, and I'm still not in either. So I'll just go over the basics because they'll be helpful later in the presentation as well. What we can do is we can define we can put our system constraints in some function f, and from that formulate this Lagrangian function L, given by our payoff function v plus lambda times these constraints. This lambda is called the Lagrange multipliers of the system. These are sort of these hidden variables which don't really have a physical interpretation, but they're just functions of time, the same as our size, thetas, k's, and kappas. They're just first order. So what we can do is we can solve what's known as the Euler-Lagrange equations with respect to lambda, psi, and kappa in order to obtain these three optimal conditions which need to be satisfied by any optimal control or state of the epidemic. When we solve with respect to lambda, we just simply return the SIR dynamics, so that one's fairly easy. When solving with respect to kappa, we obtain this optimality condition, which needs to be satisfied at the optimal control. And when solving with respect to the state, psi, we end up returning this equation for the Lagrange multiplier dynamics. It was important to make that distinction between solving with respect to kappa and solving with respect to k, because this is the point at which we Nashify everything. We find that Nash equilibrium, and then we solve these equations together. Now, typically when I give this presentation, I don't exactly go into the details on how we solve it. I will briefly here because it will be relevant later. I'm making too many promises here. So we can solve these equations together using a forward-backward sweep ODE method. And the algorithm goes a little something like this. We make some initial guess for the control kappa. And with that, we can solve forward in time the state of the epidemic because we know the initial time condition, that is just one person is being infected. What we can then do is we can solve backwards in time the Lagrange multiplier dynamics. This end time condition on the lambdas comes from the fact that numerically we can't integrate our utility all the way to infinity. We have to cap it at some maximum time, which we call TF. So just trust me that if we know the form of the utility, we can calculate what this end time condition is. And so with this calculated state and Lagrange multiplier, we can then solve that optimality condition in order to find some new guess for our kappa, which we can then just loop this around until two iterations are relatively close, at which point we just say it's converged. That's all the boring technical stuff. Now we actually get some plots. So this is what, when we solve for these different utilities, these are some of the plots we get. And intuitively, I think they make sense. So what I've shown here is the optimal disease dynamics for 4 different utility functions, each corresponding to a different cost of infection, ranging from a relatively light disease in the purple to a more severe disease in the red. And as you can see, especially looking at the control graph down here, again, it's fairly intuitive. The more severe the disease, the more you're going to social distance by reducing your kappa. You're going to do that earlier, and you're going to keep up that social distancing for a lot longer. This also then results in a lower peak of infection and also less people being infected in total by the end of the epidemic. So that's the sort of first half of the session. So this is a good point to come back in if you've fallen asleep. And yes, I've made that joke multiple times. So what we've done so far is we've gone from having some analytical form of the utility that people are optimizing for, and then solve the related constrained optimal control problem in order to obtain these Nash equilibrium SIR dynamics to optimize for these utilities. And these sorts of problems are not so much fairly well studied in epidemics, but these sort of optimal control problems are fairly well studied in general. You can consider different types of utility, different disease models. I've just shown one for the sake of this presentation. The sort of real goal of my PhD is to try and work in the inverse direction. What if it were possible to observe some given disease dynamics and from that be able to infer some hidden cost or utility function that's being optimized by these disease dynamics? I think this would give us great insight with how people react in the face of epidemics. We could see like what their priorities are, what they perceive as the cost of being infected versus the cost of social distancing is. We propose to do that using a new type of physics-informed neural network, which we're calling Nash neural networks. We've sort of based this a lot off of 2 papers, one you can't see because of the taskbar, called Lagrangian neural networks and Hamiltonian neural networks. The basic idea I'll go over in the next slide. I forgot to put this one in. So essentially, there's 3 different tasks that we would want this method to complete. First of all, we would want it to train purely on observable data. I mentioned that these Lagrange multipliers are necessary for the optimization, but if we ever want to use this method on real-life data sets, these aren't visible. So we want some way of being able to train our neural network without them. We also want it to assume nothing about the form of the utility. That's why we use a neural network, because the only assumptions we're making are what the inputs are. We don't want to say, oh, this variable could be linear in this term or quadratic in this term. We want as general a method as possible. And then also we want one which isn't dependent on the specific system dynamics, i.e. our specific SIR dynamics. We want it to, again, you could put any system dynamics into this method and it still work just as well. Our current working method falls into this category. So it assumes nothing about the utility, and you can use it with any system dynamics. However, it does rely on knowledge of the Lagrange multipliers in order to train the network, which means we can test this method on generated data sets, but not yet on real-life data sets, which is the big goal. So to go quickly over how this method works, so to revisit our Lagrangian mechanics quickly, before we had this analytical form of the utility V, what if we were to just simply replace that with a neural network? At that point, we get some network schematic that looks like this. So our inputs to the network are those dastardly Lagrange multipliers and the state of the epidemic, which is definitely observable. And so we can plug that into some neural network which corresponds to our utility function. And with that and some given SIR or other system dynamics, we can formulate our Lagrangian function, solve for the Euler-Lagrange equation, and get these free conditions as before, except now they represent these free auxiliary neural networks with these outputs that we're able to train against. Again, we're assuming we know lambda here, so if you know lambda, you know lambda dot as well. And so yeah, and then we have psi dot and the optimal control, which we assume is observable as well. So when we code all of this up, we get pretty good predictions for these outputs, but that's not what we're interested in. What we're interested in is how well we're able to predict the output of this utility here, which means I have the great joy of trying to represent a 5-dimensional function in 2D plots. So what we can do, so the results I'm about to show you are for the alpha equals 10 case, cost of infection of 10. What we can do is we can split up the utility into the cost of social distancing and the cost of infection term. Whilst I've shown the social distancing term as a 3D plot here, I think it's perhaps clearer if you have these side-on views. So you can see the dependence on kappa, psi s, and psi I. And essentially in the blue line, we've shown the analytical form of the utility, the psi s kappa minus kappa star squared. And the dots are the training data that we use to train a neural network, evaluated on the neural network. And as you can see, all three dependents show pretty near perfect alignment with the analytical form of the utility, which I think is pretty cool. But we want to ideally be a little bit more ambitious than this. Instead of just evaluate our neural network on training data, how well does it extrapolate to data which we didn't train against? So what we can do is, instead of taking side-on views of this 3D plot, we can instead take contours of it, which I show here. So if you look at this first panel, for example, here each data point, I should say, is a slice in time of the epidemic. So each data point comes with a sort of triplet of psi s, psi I, and kappa. So what we can do is we can take one data point, for example, on this green line here. We fix psi s and psi I, but then vary kappa, both analytically in this function and on the neural network. And so we show that here for 3 different data points. And again, you see pretty well, like near perfect extrapolation, at least on these data points, when you extrapolate with kappa. When you extrapolate with psi s, slightly less good alignment, but hopefully we will work on improving these results. And even then, like, this could be all over the place. The fact that it's still at least almost linear, even though it's clearly not, I think is still a good work in progress. And then again, for the dependence on psi I, this is the actual range of the training data. So it makes sense that beyond that, the neural network prediction goes away from what we would analytically expect it to be, considering if we actually did have a data point of psi I equals to 1, that means everyone is currently infected with the disease, which is probably unrealistic. So ideally, if you had no knowledge of the analytical form of the utility, you would look at this line, look at where the training data is, and in that region be like, okay, it's linear in that region with a gradient of 10, so we can assume that people associate a cost of infection of -10 with this particular disease. So that's all well and good. I know I've only got a couple minutes left, so there's only a couple more slides. As many of you know, I have spent a large proportion of my year studying in Japan. Some of my collaborators for this project are in Kyoto University, so I thought I should at least provide a quick update as to what I actually did over there beyond just take loads of holiday. So as I said, this Nash neural networks method currently falls within this region of the Venn diagram. However, whilst I was over there, we did actually at least theorize some methods which could fall into the other categories. So one which is dependent on the system dynamics is one where we directly integrate out the Lagrange multipliers. However, this uses knowledge of our specific SIR dynamics, so that's not really ideal. And then in this category, we assumed something about the utility, which essentially said that people, instead of having knowledge of the whole pandemic, only have knowledge of the next day or two. This is called strong discounting, which could be considered quite realistic as well. Admittedly, I haven't looked at this method since the spring, so please don't ask me too much about that one. But then the most recent one that we've come up with is one that hopefully falls right in the middle, which would be ideal if we could get it to work, which we've called AFBS-NNN, which stands for Adapted Forward Backward Sweep Nash Neural Network, because that's not a mouthful. So just briefly how we hope this method will work. So our current working Nash neural networks had these three optimal conditions which gave predictions for lambda dot, psi dot, and kappa opt. What we could do with them is we could just bung them through a forward backward sweep as we had before. The only problem with that is we're assuming that we don't know nothing about the Lagrange multipliers, so we don't know what this end time condition on the lambdas is. So what we can do is we can create some function which runs the forward backward sweep method given some input lambda TF, end time condition on the lambdas. This will then give some output prediction for the state, the Lagrange multipliers, and the optimal control, from which we can then create some loss function to train against, like some squared loss function comparing this prediction with the actual data set we have, and from that find the end time condition on the lambda, which minimizes this loss. I mean, if this works, this will be great, but there are certain pros and cons. The obvious pros are the fact that it falls right in the middle of this Venn diagram, which would be the ideal solution as such. The abundant cons to this method at the moment is that it's very, very computationally expensive, as in there's a gradient descent inside of a gradient descent inside of a gradient descent at the moment. So, there's certain things that I'm working on at the moment to try and reduce this, the idea of having a pre-trained neural network instead of random initialization, choosing reasonable initial guesses for both kappa and lambda TF, and also just generally being better at coding than I currently am. So that's the sort of current state of my PhD as such. I've focused more so today on the reverse problem with the Nash neural networks of inferring the utility from disease dynamics. However, we are doing a lot of work on the forward problem as well, this idea of what exactly people are optimizing for and what exactly it means to be a rational individual. So, for example, it could be realistic to say that people behave differently depending on if they're susceptible versus on if they're infected. You could also say that both young and old people will not only behave differently, but also have different utilities, different priorities. There's probably a much higher cost of infection if you're old compared to if you're young. As well as that, I think that people don't necessarily think as selfishly as the Nash equilibrium. So, if you think back to COVID, you didn't just care about yourself being infected, you cared, or hopefully, cared about your family being infected as well, perhaps your friends, perhaps your work colleagues. At this point, we're getting into some ethical territory as such, which me as a Christian finds really interesting. So I'm giving a talk on this in a few weeks' time, more so focused on the forward problem of my PhD. This idea of why would you want to prioritize others almost over yourself, I think has some applications with the quote golden rule of ethics to love thy neighbour as thyself, or to treat others as you would like to be treated. So if the forward problem sounds interesting to you, then I'll be giving this talk in about a month's time on sort of like how I think specifically Christ's teaching, but then also like other ancient religious teachers on this rule, how they potentially affect my PhD as such, and this idea of what people want to prioritize. Don't worry, quick plug over. I would like to thank my supervisors for this project, both the ones from Warwick and the ones in Japan, as well as the various people who give me money. And I'll happily take any questions that anyone may have about that. Thank you.